Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this video is to review OpAmp circuit analysis. And in my Circuits 2 video lecture series, we are going to be looking at OpAmps in a fairly detailed way. We're going to look at an internal circuit model for an OpAmp. We're going to talk about the role of feedback networks in OpAmp circuit design and how feedback works, basically. But the purpose of this video is to review circuit analysis of OpAmps as you would have seen it in probably your very first circuits course. So there are just kind of some rule of thumb things that you can use for OpAmp circuit analysis that allows you to very quickly understand how an OpAmp circuit will work. And what I'd like to do is review those rules. And so what I've got here is a drawing of an OpAmp. Of course, we represent an OpAmp as a triangle with a positive terminal and a negative terminal. This is ground. And in this analysis, our output voltage between the output of the OpAmp and ground is denoted as V out. The voltage applied to the negative terminal, I'm going to denote as V minus. The voltage applied to the positive terminal, I'm going to denote as V plus. And we're also going to talk about the current, or the lack of current, I guess more specifically, flowing into these input terminals. And so I'm going to say that the current flowing into the positive terminal, I'm going to denote that as I plus. And the current flowing into the negative terminal, I'm going to denote I minus. And so there are basically two rules of thumb for OpAmp circuit analysis. The first one is that we assume that no current flows into either of the input ports. So I plus and I minus are both equal to 0. And we also assume, somewhat magically, that V plus is always equal to V minus. And so there's just something about an OpAmp such that we can always assume that it forces our circuit to behave in such a way that the voltage at the positive terminal is equal to the voltage at the negative terminal. I'm not going to explain why that is. That's the purpose of the lectures that I have coming later on in my Circuits 2 series. And so let's just take this as a given for now, and we'll use these rules in circuit analysis. And if you're curious about where this comes from, and you should be, I think, watch my later on video in the Circuits 2 series about OpAmps. In particular, this was always kind of a big misconception for me as I was learning circuits. I always thought that there was something going on inside this little triangle that forced these two voltages to be the same. And it turns out that that's not the case at all. This is a result of hooking up the OpAmp in a feedback configuration. And I'll talk more about that in the other lecture. And so what I'd like to do is just do 3 circuit analysis examples: a non-inverting amplifier, a voltage follower or buffer circuit, and a summing amplifier, using these rules just so you can see how that they are applied. Okay, so the first example we're going to work through is a non-inverting amplifier. And of course, the purpose of an amplifier is to make a signal bigger. And the way that we measure that is by calculating something called the voltage gain. So voltage gain, often we represent that with the letter G. And it's equal to the ratio of the output voltage to the input voltage. So if the voltage gain is 2, that means the amplifier doubles the voltage of the signal that we pass through it. And we control the gain of the amplifier by adjusting these two resistors. And we can figure out exactly how that works by applying Kirchhoff's voltage law, basically just a voltage divider. And so we want to come up with an equation that is a function of the output voltage and the input voltage. And we know that the current flowing into this negative terminal is 0. And we also know, so I guess we know let's call this voltage V1. So the voltage at node V1 can just be calculated using the voltage divider rule, because the output from this node to ground is V out. And so V1 is equal to R1 over R1 plus R2 times V out. And we also know that V1 happens to be equal to the voltage at the negative terminal, V minus. And we know that the OpAmp and this network will work to keep the voltages the same at the positive and negative terminals. And so V1 is equal to V minus. It's also equal to V plus. And V plus just happens to be the input voltage that we're applying to this terminal. So it's equal to V in. And so that means that the voltage gain, V out over V in, is equal to R1 plus R2 over R1. Just solving this equation for the ratio of those voltages. Or, as is more commonly, it's more commonly expressed as 1 plus R2 over R1. And so basically the ratio of these two resistances control our gain. If we want to have a gain of 2, for example, this ratio would be equal to 1, and we get 1 plus 1 equals 2. If we wanted to have a gain of 3, R2 would be twice as big as R1, and so on. So the next example is what we call a voltage follower or a buffer. And basically the purpose of a voltage follower is to create a circuit with an op-amp where the output voltage is exactly equal to the input voltage. And you might say, well, what's the point of doing that? It's usually for circuits that require it's usually for circuits that are driving a load that requires a large amount of current. So for example, if you're generating your input voltage using a digital to analog converter, usually digital to analog converters can't supply a lot of current to a load. And let's say you want to then use that voltage signal and drive perhaps a speaker, which actually requires a fair bit of current. What you would do is you would put a voltage follower in between your digital to analog converter and your speaker, and you would select an op-amp that's able to supply a lot of current. And that way you could meet the current requirements of your load. And so how we analyze this, well, because we've basically directly connected the output voltage to the negative terminal, we know that V out is equal to the voltage at the negative terminal. We know that the voltage at the negative terminal is equal to the voltage at the positive terminal. And we know that the voltage applied at the positive terminal is equal to V in. And so V out is just equal to V in. So we get no change in voltage, but we get superior. We get a superior ability to drive more current into our load. So the final example is something that we call a summing amplifier. And basically the purpose of a summing amplifier is, as the name suggests, to add a bunch of signals together. In this case, we have 3 voltage signals that we want to add together. However, you could have just 2 branches here, or you could have 4 or 5, or basically as many as you want. If you wanted to add another branch, you would just put another branch down here and add another resistor, for example, R4. And this is the kind of thing that you would use to, for example, combine audio signals, right? Like if you were mixing a bunch of audio signals together and you wanted to do it in an analog rather than a digital way. And the way that we analyze this circuit is we define the current through this first branch as I1, the current through the second branch as I2, and the current through the third branch as I3. Let's define the voltage at this node as VA, and of course the total current flowing through this branch I. by Kirchhoff's current law, I is equal to I1 plus I2 plus I3. Now, to write an equation for what these currents are equal to, the first thing we can do is write an equation for the total current I. And the total current I is, because the total current I flows in this branch, it can't go into the input terminal of the OpAmp because no current flows into an OpAmp. So basically, this current has to flow through this resistor. And by Ohm's law, the current through this resistor is equal to the voltage difference across the resistor divided by the value of the resistor. And so this is equal to VA minus Vout divided by RF. That's equal to the total current. Now, similarly, we can write equations for the current in each one of these branches. So the current through the top branch, I1, is equal to the voltage we're applying minus VA. So I1 is equal to our input voltage, V1, minus VA divided by R1. And similarly, I2 is equal to V2 minus VA over R2. And I3 is equal to V3 minus VA over R3. And so now to simplify these equations, what we can do is substitute this term in for I, this term in for I1, this term for I2, and this one for I3. But we can simplify our equations a little bit before we do that. Notice that our voltage VA is equal to the voltage that we're applying to our negative input in our OpAmp. And of course, the OpAmp works so that V minus is always equal to V plus, but we short V plus to ground. And so this is equal to 0. And so basically VA goes to 0. Whoops, that was the wrong voltage. VA goes to 0 in all of these equations. And you might say, well, wait a minute, like, you know, since we're basically shorting this voltage to ground, how does any signal get out of this OpAmp at all? Remember that the voltage at this point is 0, but the current is still flowing, right? We've still got this total current I that is flowing through this branch and then gets redirected to flow through RF. And it's the current flowing through RF that basically generates the voltage Vout. So if we remove all these VA terms and substitute it back into our current equation, we get minus Vout over RF is equal to V1 over R1 plus V2 over R2 plus V3 over R3. And I can rearrange this a little bit and write Vout is equal to minus RF over R1 times V1 plus RF over R2 times V2 plus RF over R3 times V3. And so you can see what we've got here at the end is our output voltage is equal to the summation of V1, V2, and V3. We've got a negative sign here, but that just means this is an inverting amplifier, which is not a big deal, particularly for audio applications. And not only that, we can adjust the relative weight of each of the signals in our summation by playing around with these resistors. RF is common, but then we can adjust R1, R2, and R3. So we could make these three resistors variable resistors, like we could use potentiometers, and that would allow us to increase the volume of one of the signals and decrease the volume of others.